Thank you so much. So today I'll be talking about analyzing and simplifying privacy policies at scale. Um, and thank you for the introduction. And I think I always start with this question, what is a privacy policy? And privacy policies are these legal documents that organizations use to disclose how they collect, share, analyze, and secure their users' personal data. So this is the only source of information that any internet user can get about what is happening with their data online. And for this reason, a lot of regulations, such as the GDPR, that is the General Data Protection Regulation, and CCPA in the United States, that's California Privacy Act, make it mandatory for organizations to make their privacy policies readily available to their users. And we have seen that in the last few years, more than 182 legal jurisdictions around the world have created and enacted some form of privacy laws globally. And this number, like I said, this number has grown exponentially in the last few years. But the thing is, people don't read privacy policies. Most of the time, when I talk to people, I have to explain what a privacy policy is. And even when I started this research, I didn't really know what a privacy policy was, and I had definitely never read one. But now I've read quite a few, and my thesis is on this topic. So although people say that they care about their policy, about their privacy online, they don't read the policies. So the onus to protect user privacy often falls on regulators. But regulators are also overwhelmed by the number of privacy policies on the web. And so it becomes essential that even though not a lot is happening in order to protect user privacy online, it is essential that organizations make their privacy policies accessible to the users. So at least those users that do care about the policy and go and read the privacy policies are able to access them. And so to understand the privacy policy landscape online a little bit better, and to apply NLP techniques to simplify these policies to make it more easily readable for users, we created a privacy policy corpus. So I'm going to talk about the policy creation pipeline. Then I'm going to talk about a couple of tasks that we performed on privacy policies. Then finally, I'm going to end with a task that we recently have been working on, which sort of tries to make the policy readable to users in a way that they don't have to spend almost any time on it. So in order to create this policy pipeline, what do? We found that companies put a link to their privacy policies on the footer of their of the landing pages online, and this is for website privacy policies. There are also app privacy policies which are made available through Google Store, Apple's Play Store, etc. And this makes the task of collecting them a bit hard, especially for the website privacy policies. And that's because we'd have to go to each and every website and then collect the policy. So we came up with an approach to do this automatically. And this is our collection pipeline. I'm going to walk you through each of the steps in this pipeline a little bit better. But just as an overview, instead of going to each website, we started with Common Crawl. So Common Crawl is this open source web crawl which crawls the web every month and releases an archive of the crawl. So we simply collected the URLs which satisfied a URL selection criteria for it being a privacy policy. Then we went through a filtering process, a crawling process, a language detection step, a content extraction step, a document classification step, finally duplicate removal and near duplicate removal steps. And finally, we ended up with about 1 million privacy policies. So this was our first crawl. We have since crawled had about 3 more crawls to the web. So we have around 3.4 million privacy policies at the moment. So like I said here, if you look at this page, this is sort of an example of the different types of policies in the world. And here you can see that they are, of course, in different languages. And the pages also have content which is uh, not just the policy. So there are headers, there are footers, navigation menus. Sometimes the cookie policy is embedded within a privacy policy. Other text within the page might also be uh, in the same page. So in order to get all this removed, we went to the scrolling, this document filtering process. So first of all, why we start with Common Crawl? It's because Common Crawl releases this monthly crawls, and each of these monthly crawls is sort of a snapshot of the web. And we downloaded one such snapshot which contained 2.6 billion URLs. And then instead of crawling each website, like I said before, we applied this URL selection criteria. We found that privacy policy URLs tended to have the words privacy or the words data and collection in them. So we just extracted those URLs which had these words. And to evaluate this criteria, we just looked at the privacy policies within the OP 115 corpus. The OP 115 corpus is this corpus of privacy policies which with fine-grained annotations. But we just used this as a test for our selection criteria and found that this criteria had a 92.17% coverage. Although this is not 100%, for our use case, it doesn't really matter because we wanted a snapshot of the web, and 92% was enough. For the document filtering step, we sort of used open source packages, especially for the language detection step. We used this Python package called langID and selected only English language documents. Then we use boilerplate, which extracts the content on HTML pages by removing things like the header, footer, and navigation menus. And so we applied this on the crawled policies. Then we wanted to know that the documents we crawled were actually privacy policies, because if you remember, we simply crawled all of the documents that satisfied this URL selection criteria. So we randomly sampled 1,600 English language documents from our crawled set. We manually labeled them. 1,145 were privacy policies and 455 were not. And we trained 4 supervised models to make this classification. One was URL based, where we applied TF-ID of extracted features on the URL. The other one was document based. Again, TF-ID of features based on the text within the document. The third was a combined model where features from both the URL-based model and document-based model were combined together. And finally, we used Roberta, and we used the first 512 tokens within the document. And here you can see that Roberta sort of beats everyone else. But the combined model does pretty well as well. And you can also notice here that the precision recall and F1 scores are pretty high. Even though this is the case, this is the case because most of the web crawled sites which are not privacy policies did not look anything like privacy policies. When we only look at things like terms and conditions and cookie policies and things like that, we have it's more difficult to make this distinction between a privacy policy and other sorts of legal documents. And the false positives here and false negatives here are exactly those, that is terms of service documents and cookie policies, etc. So I'll go on a little bit of a tangent here and talk about how often policies were unavailable when we did this crawling, and why they were unavailable. So when we crawled, we found that, let me go back to my my pipeline here. And here you can see at the crawling step, we found that some URLs were errors. And here we are only looking at the errors within those crawled documents. We found that 79% of the errors were HTTP errors, and then followed by not supported, DNS lookup errors, TCP timeout errors, etc. And most of the HTTP errors here came from the page not 404 or page not found error. And that indicates that although the link is valid, although the crawl was valid, the page was unavailable from the side of the company. And so um, given that, we determined how many privacy policy URL links might be dead or unavailable, and we found that about in 1.37% of all the policy links, um, of all the privacy policy links, about 1.37% were unavailable. And here you can see issues indicating policy unavailability and other indeterminate issues. By indeterminate issues, we mean issues that might have cropped up because of our crawling technique, problems with the crawler, problems with the operating system when we use the crawl, etc. Next, we looked at natural language discrepancies. So if you go to a website and the website is offered in English and Spanish, you would expect that both English and Spanish users are using the website. And so the policy should be offered in English and Spanish as well. And so we checked if this was the case, and we randomly sampled 250 successfully crawled URLs. And we found that 41.9% of the websites that are offered in multiple languages have some sort of language inconsistencies. And in general, about 5.2% of all websites display some sort of language inconsistencies. Non-policy content. So let's say that you click on, a user clicks on a privacy policy URL and is taken to a page. How often does the user encounter content which is not the policy itself? To find this, we randomly sampled again 500 documents, and we found that 6.8% of the documents in the sample had empty content on the policy page. More specifically, we found that the heading said privacy policy, but there was no content of the policy itself. Additionally, we found that about 2,858 were in Latin, which is not a language which is used officially in any jurisdiction. And so totally about 1.23% of valid English language privacy policy URLs has empty content, was our conclusion. So let's take the example of a particular user who lands on a website, right? A user arrives on the website, and first we found that there is a 34% chance that only a 34% chance the user would find a privacy policy URL. Then even if he finds the URL to click on, there is a 1.37% chance that it leads to an error page. Then even if it doesn't lead to an error page and the user is actually taken to a page that is valid, there is a 1.23% chance that the policy has no content. And finally, even if it does have content, there's a 41.9% chance that there is a language inconsistency. So all of this is to say that policies are often unavailable. And another small tangent is how we estimated the total number of policies on the web. So what we did here was we crawled about 1 million policies. And our plan here is to apply NLP techniques to make these policies more readable, these policies more accessible to regulators, etc. But we also wanted to see the number of policies that we didn't get. And so we use this technique called capture recapture. The capture recapture technique is often used to estimate the sizes of populations of animals. So let's say you are in a forest and you want to estimate the total number of this special type of rabbit. You can't just start at one point and go around counting all of them, because they move around, and it is pretty hard to make sure that you capture all of them at the same time. So capture recapture is a technique which makes it easy to estimate the number. In this technique, you first capture a set of animals, you mark them, you release them back into the wild, you go back another day, and you capture another set of animals from the same population. Um, and then you count how many of the previously marked animals were captured in your second set. And then an estimate can be made of the total population of the animal. There are some assumptions to using this technique, and I won't go into this right now, but you can look more into it based on your use case. And all of these satisfied the privacy policy use case. So we made two different crawls. The first crawl had 1 million policies, which we counted as a marked sample, and we made another crawl of 600,000 policies, which we counted as recaptures. Um, and then we estimated the total size or total number of, we estimated the lower bound of the total number of English language documents on the web of around 3 million. Okay, so I think coming back to the main topic here, we collected a corpus which contained about 1 million policies from about 1 million domains. The mean word length of each policy document itself was 1,871. Domains such as .com, .org, and .net made up 63%, 5%, and 3% respectively. And we also had other country level domains. And these documents also had a pretty high average Flesch Kincaid grade level, which is the number of years of US education required to understand a policy. And it said 14 years, which comes to around college level, whereas a average internet user is at a high school reading level. So all this is to say that policies are difficult to read, they are long, and that's why people don't read them. And so what do? The policies have this wall of text, and NLP techniques can be applied on these policies to make it more readable, more accessible, and for people to understand them better. And to do this, a lot of prior work had been done on question answering within policies, classification tasks, NER tasks, etc. But most of them had inconsistencies in scaling, and they often did not perform very well. And since we had collected this large corpus of policies, we decided that creating a privacy policy language model might help tasks within the policy domain. So especially because in-domain language models perform significantly better on tasks in their respective domains. So we created PrivBert. This is the privacy policy language model to address the requirements of a language model in the privacy policy domain. So PrivBert was trained starting with Roberta for 50K steps and a batch size of 512 using gradient accumulation for a period of 8 days. And we tested PrivBert on 2 tasks in the privacy policy domain, namely the data practice classification task and the answer sentence selection task. So this is the data practice classification task. It's a multi-class, multi-label classification problem first introduced in the OP115 corpus. And here is an example of the OP115 corpus and the classes that it can be classified into. So the OP115 corpus has 115 privacy policies segmented into paragraph size sections, where each section can contain information about one or more data practice. And here you can see an example from the OP115 corpus, and the text here is a section from a privacy policy, and the classes for this section are data security, user choice and control, and first party collection and use. And so we tested this task on PrivBird, Roberta, and Policies, which was an LSTM-based model, and we found that PrivBird performed best across all of the classes. You can also see from the support column that the number of samples in the test is rather low for some of the classes. And this is because op115 corpus has only 115 privacy policies, and some of these classes do not occur often. Additionally, it is hard to annotate privacy policies because they are written in legalese, and legal scholars are often required to make these annotations. However, we still got a pretty good precision recalls and F1 scores, and we found that PrivBird beat Roberta and Policies as well. Next, we tested a question answering task from the privacy QA corpus, and here the task was an answer sentence selection task to determine the relevance of a user question. So the privacy QA corpus consists of 1,750 questions about the contents of 35 privacy policies asked by crowd workers based on public information about applications on the Google Play Store. Legal experts then identify the relevant section within the policy for each question. And here you can see an excerpt from the corpus itself, where the segment is a sentence from a privacy policy. The query is asked by a crowd worker about the privacy policy, and then the label is whether that segment is relevant or irrelevant for that query. And once again, we find that PrivBird performs better than prior tasks, where here you can see the precision, recall, and F1 scores. So these were the two tasks that we used to test our language model. But other than that, there is no real way, and both of the tasks that we use aren't really a good way for users to understand what is happening with a privacy policy. So we started looking at other directions to make it easier for users to understand what is happening with their data. And that comes, so here I come to TOSDR, or Terms of Service Didn't Read. This is a website which takes privacy policy documents and terms of service documents and crowdsources annotations for them. By which I mean that in the TOSDR platform, any user can go online, sign up, and look at a privacy policy, look at data practice cases that the website has previously discovered and defined, and make comparisons between a policy itself and previously defined data practice tasks. So on the right here, you see an example of something on the TOSDR platform. So on the TOSDR platform, the privacy policy of YouTube has been looked at quite often, and the sentences below YouTube, you can see are the data practices defined by the TOSDR platform itself. And when you click on one of these, it takes you to another page where different users have identified this as identified with different sections within the privacy policy as matching with one of these predefined sentences. So for example, this service can view your browser history is a sentence which is defined by TOSDR. And when you click on it, different parts of the privacy policy of YouTube which has association with the sentence, is mapped. So and also, when a large number of these mappings have already taken place, the TOSDR platform then goes in and gives the policy a letter grade, um, by which I mean they grade privacy policies between A and E, where A is most privacy preserving and E is least privacy preserving. Here you can see that YouTube gets grade C. Um, and policy letter grades provide a convenient means for users to evaluate website data practices. And they don't really have to spend a lot of time. They don't have to ask questions, as in privacy question answering. And in the cases that users don't really want to know about privacy policies, but only want to know in cases where a policy is using very predatory data practices, a letter grade would be perfect, because then a user would see that a letter grade is E or F, and then they could come in and look at what the issues with the policy are. And this is currently being done in a crowdsourced manner. So this is very hard to scale. And we attempted to apply NLP techniques to make this a little bit more easier, either for the crowd annotators and eventually for automatic annotation as well. And like I said, the adoption of letter grade remains limited due to the time-consuming nature of policy annotation and frequent updates to privacy policies. And additionally, once a crowd worker has come in, or a internet user has come in and annotated a policy and matched it with a segment within TOSDR, a TOSDR moderator comes in and either approves or rejects that annotation, and so integrity is maintained within the website. Yeah, so in the TOSDR platform, each data practice is deemed as a case. So here you see everything under YouTube are different cases. For example, the service can view your browser history, your personal data is used for advertising, are two different cases. And TOSDR contains about 130 privacy policy related cases, and annotators match text segments from privacy policies itself to one of these predefined cases. And we scraped the policy segments for each case. And for one case, we found that a minimum of 2 different policy segments existed, and a maximum of 755 policy segments existed from different privacy policies, with an average length of 32. By which I mean, let's take the case, this service can view your browser history. Then one of the matching would be from that of the YouTube privacy policy, another could be from Meta, another could be from DuckDuckGo, etc. So that is what I mean by minimum of 2 and maximum of 755. So this is how the corpus exists in TOSDR. But in order to make this a problem that can be solved using machine learning, we created a data set, and we defined a problem. So some cases described within these cases were contrasting, by which I mean they attributed to the same data type, but they were different practices. Let me give you an example. So for the data practice, your personal data is not sold, there were other, which is a case, and your personal data is sold unless you opt out, is a contrasting case. And your personal data may be sold as part of a financial transaction is another contrasting case, because all of these deal with your personal data and how it is sold and in what conditions they are sold. So we manually clustered those cases that are describing the same sort of practice into a total of 24 different clusters. while the other 67 clusters had no data practices. Yeah, so here we come to the problem that we defined. So given a case and an excerpt from a privacy policy, the task is to find if the excerpt is similar to the case, where similar means whether they are describing the same sort of data practice. And the annotated case segment pairs serve as positive training samples. And to collect negative training samples, we use three different sampling techniques. First was a cluster agnostic sampling, where each cluster contains different types of data practices. Within cluster sampling, where each cluster had contrasting data practices, and combined sampling, where we looked at both within and outside. And we trained a model using multiple different negative samples while disallowing duplicates. And the way we did this was we concatenated the case and the segment separated by a special token and used it to fine-tune PRIBBERT. We used a binary cross-entropy loss function. And here we find that so we trained it on three different models, of three different sampling techniques. The first was the cluster agnostic sampling. Second was the within cluster sampling and the combined sampling. We found that the cluster agnostic sampling performed best, followed by the combined sampling. The within cluster sampling did not perform very well because we believe that in this case, the segments of policies that and the cases differ a lot. And so when during testing time, the model is not really able to predict very well when they are similar. And here are some of the results. We found that the performance on the singular practice set was superior to that of the contrasting cluster set. Here, by singular practice set, I mean we had created two sets of two held out sets. One was a set which contained samples from multiple clusters. One was a set which contained samples from the same cluster. And we found that the performance on the singular practice set was superior to that of the contrasting cluster set. Secondly, we found that identifying dissimilar pairs consistently improved with increase in the number of negative samples, but with a negligible deterioration in identifying similar samples. So increasing the number of negative samples was the best thing to do. And here I believe that we used 5 times the number of negative samples as that of the positive samples. And the number of dissimilar pairs would significantly outnumber the number of similar ones in a real world setting. Thus, deployed models should be trained robustly on dissimilar pairs. And while false positives would mean additional annotator effort, false negative predictions would be challenging to identify due to lack of an active feedback loop. By which I mean, whenever a model is negatively or positively identifies a dissimilar case and segment, then it is easy to spot that this is not a matching set. But the ones that are not identified would be harder to catch because there is no active feedback loop. And finally, we performed a case study to simulate real world conditions. And in this, we simply took one privacy policy, and that of Airbnb. And the first authors of the paper reviewed the policy and annotated each TOSDR case for that policy. So we split the policy into 150 segments, encompassing paragraphs, section titles, and item lists. And then we applied the combined sampling model to measure the semantic similarity between each case and segment combination. And here we found that we found a precision of about 0.63, recall of 0.8 for the true class, and precision of 0.81, and recall of 0.64 for the false class. And this is how the model could be deployed. For example, let's say the selected case is your personal data is used for advertising. Then the model would be able to go in, look at each segment within a privacy policy, and match which segments within the policy are similar to the case presented here, with that the personal data is used for advertising. And in the case that TOSDR is the first step of this problem would be to deploy it within TOSDR, where annotators can use this in order to make the distinctions. The second step would be automatic annotation once more training data is collected. And yeah, so that is about it. And for future work, we are thinking about a privacy policy search engine. We already have deployed a privacy policy search engine. I can share the details of the link of the search engine itself. We're also looking at extracting personal information types from the privacy policy itself. For example, policies often mention that they collect name, address, social security number, etc. So we want to know what data types the policy is saying that it is going to collect from the users. And also we plan to look at how to extract unusual sentences from privacy policies. Here, unusual sentences are those sentences which don't often appear within a policy, and they can be looked at since they might be different from the sort of practices that are often conducted within privacy policies. So yeah, thank you so much. Thank you for inviting me. I can answer any questions.